Hi, welcome to video 9.4a, direct comparison test. So 9.4 has both the direct comparison test, which they call the comparison test, and the limit comparison test. The direct comparison test is a little bit more difficult because you have to prove an inequality as part of the process. Limit comparison test, instead of proving an inequality, you have to find a limit, which is easier. They'll tell you which test sometimes to use, otherwise it'll be up to you. Both of them have the word comparison in them because you're going to have to come up with a series to compare the given series to. So you're going to be given a series. You'll call that series UN. It's got to be a series of positive terms. So write out the first few terms and just state the fact that yes, they are all positive. Then you're going to have to come up with a series VN that you're going to compare it to. We'll talk about how you're going to do that. You're going to then check to see whether that series Vn, which is going to have to be a series of positive terms, you're going to have to check and see whether that series is convergent or divergent. And therefore, you're going to have to compare it to a series that you can easily decide is convergent or divergent. So like a geometric series or a p-series, that kind of thing. If it turns out that the series Vn that you're comparing to is convergent and, emphasis on and if your UNs you can show are all less than or equal to those VNs for all positive integers n, then your original series, your given series, is also convergent. If the series you're comparing it to is divergent, and you can show that all of your UNs are greater than or equal to all of the VNs for all positive integers n, then your given series is divergent. So I think it's easy to remember because if the series Vn converges and each of your terms is smaller than each of these terms, it would make sense it would converge. If your series Vn diverges, then it would make sense that if each of our terms is even bigger than each of those terms, that our series would diverge. Okay, now strategies for deciding on the mystery series Vn that you will compare the given series Un to. It needs to be a series that we can easily determine its convergence or divergence. So as we discussed, like a geometric or a p-series. So for example, if you had a given series of, say, 1 over 3n squared minus 4n plus 5. What you're going to do in both the numerator and denominator is look at the leading term, so just ignore the others. Look at the leading term and ignore its coefficient. So in this case, we'd be left with 1 over n squared. Okay. Over here, again, take the leading term, 3n, get rid of its coefficient. We'd have 1 over the square root of n, which is 1 over n to the half. And finally, if I had this, I take the leading term over the leading term, get rid of any coefficients. I'm left with 1 over n cubed. And all of these are p-series. All of them we can easily show are either convergent or divergent. So what do? We eliminate the terms that are added or subtracted in the numerator and denominator, leaving only the term of highest degree. We eliminate the coefficient of the highest degree terms, and then we reduce that fraction. So here's some examples. In 3 to 14, they actually tell you to use the direct comparison test. So number 4, this is the given series. You're going to let that series be UN. You've got to... Oh, darn. Hi, sorry about that. Telephone. Okay, so you do want to identify your given series as UN because you'll be referring to these series as UN and VN. You want to be clear which is which. Obviously, all these terms are going to be positive. Remember, we're starting at 1 and going up through positive integers, so obviously this will always be positive. Just state that fact. Okay, so what do we can compare it to? Obviously, again, we're just going to take leading term, which in this case is 1. Leading term here is 3n squared. Get rid of the coefficient. We're left with 1 over n squared. Again, you're going to need to identify that. That is a p-series. The p is equal to 2. Since the p is bigger than 1, the series converges. Now that you know that the series that you're comparing it to converges, now you know that what you want to prove is that our UNs are less than or equal to those VNs. So our UN was 1 over 3n squared plus 2. Our VNs were 1 over n squared. We need to prove that's true for all n greater than or equal to 1. Now, everything here is positive, so I can do product of the extremes, keep this inequality symbol the same, and then product of the extremes. And therefore, I end up with solve. I end up with n squared is greater than or equal to -1. Obviously, that's true for all n greater than or equal to 1. So you have to make a conclusion. You have to state the name of the test by the direct comparison test. Since summation Vn is convergent and Un is less than or equal to Vn for all n greater than or equal to 1, then summation Un is also convergent. Here's like number 8, so similar thing. Again, write out the first few terms. Notice it's not geometric. Anyways, they're all positive. We're going to compare it to a Vn. We're going to take leading term over leading term, get rid of the 5, so we're left with 3/4 to the n. That's a geometric series if you write it out. Do pay attention. That's n goes from 0 to infinity. It's a geometric series. R is 3/4. Since the absolute value of R is less than 1, the series is convergent. So again, since we're comparing it to a convergent series, we need to show that Un is less than or equal to Vn for all n greater than or equal to 0 in this case. So here's our Un, here's our Vn. Everything's positive. We can do the cross product. Remember, the order is important. It's got to be the product of the extremes on the left. Keep the inequality symbol the same. Product of the means on the right. Divide both sides by 3 to the n, subtract 4 to the n from each side, and we end up with something that's true not only for all n greater than or equal to 0, it's true for every number. And again, you have to make your conclusion.